Hello and welcome everyone to the second week of NPTEL session on the course of Foundations of Cryptography. Uh, basically, actually, last week I said that from this week onwards, we will discuss the previous week's tutorials questions, assignment questions, which are given on NPTEL website. But I actually noticed that the for first week assignment, the submission date is 7th February. So basically, still we have time for the submission deadline. So that's why I will not discuss the first week assignment today. For the next week, our tutorial date will be 10th February. So by that time, the submission deadline will be over for both week 1 and week 2 assignment, I think. So next week I can discuss the assignment questions in their exact form. So for today I will discuss the broad topics from week 3 actually, and maybe there will be connection to week 2 topics also. So week 2 was basically PRG, and I think there were this you know, uh, So, week 2 topics were modern cryptography like computational world and all, and PRG. So, we will touch those part, and also the week 3 topics, which includes string cipher, provable secure instantiation of PRG, practical instantiation of PRG, CPA security, and pseudo random function or PRF. So, we will discuss just some problems, and you can answer and ask doubt and all. So let me begin. So what I am thinking is that instead of sharing the PPT screen, I will open a whiteboard. Let me know if you can see the whiteboard, and I will try to write the questions and discuss the solutions there. So the whiteboard is visible, I think. Okay, Dharun, you are requesting to record the meeting. Okay, you can. Anyway, so the YouTube recording will be shared with you, I think. Okay. So the whiteboard is visible, I hope, right? Is the whiteboard visible to all of you? Okay. Thank you, Jitesh. So, mm, let me try to just write something. So, I am also very new to using this thing. There could be some technical issue. Also, yes, another important thing that I want to mention is that what happened last week actually. So Zoom basically allows 40 minutes meeting. So after the meeting ends, last week it happened that after the second 40 minutes slot, it took actually 10 minutes to again enter into the same meeting link. For me also, I could not start the meeting before 10 minutes. So I am just informing you that in case you see that you cannot join the meeting back, just wait for exact 10 minutes and then you check. I will be able to restart the meeting again, and then you can join in the same link. Okay. So just wait for 10 minutes. You can consider it as a break. Okay. So you can join back in the same link. Okay. That is all. And then, so let me actually write few questions for you. Okay. And then we can discuss. So here goes your first question that you have to select a correct statement from the following. Okay. So given statements are string cipher is randomized and second statement is string cipher is deterministic. Okay. Same key can be used. Uh, okay, you cannot see anything. Is it the case for others also? Whatever I am writing to whiteboard, is it visible? I am writing something on the whiteboard, the question. Visible. Okay. Okay, then I will request you to just join back maybe. Okay. To encrypt multiple message of string cipher. And last option is string cipher is single message. Yes, you will be provided with the recording. It will be done from the NPTEL authority itself. So, so here is the question. Uh, which one among the statements are correct? String cipher is randomized, string cipher is deterministic. Same key can be used to encrypt multiple message of string cipher or same and string cipher is single message CPA secure. You can unmute yourself and answer, or you can also write in the chat. Second option is correct. Yes, you are correct. Second option is correct. There can be multiple correct options as well. You can check for them also, if there is. So, okay. Is there any other correct statement? Achha. Third one you were saying it is correct. Okay. Okay. So, okay, let me discuss the answer then. So, only second option is correct actually in this case. Only second option is correct. Why, that we will see. So, stream cipher, what is stream cipher? Let us just recollect. If I go to say next page, okay, let me go to next page. So, what is stream cipher? So stream cipher is viewed as practical instantiation of PRG. So theoretically, theoretically, PR, uh, PRG is pseudo-random generated, right? So uh, there you actually specify some input space, let's say M. Okay, so this is your PRG seed length, right? And you produce output of some L of M length with the condition that L of M must be greater than M. So your output length of PRG must be greater than seed length of PRG. Okay, and this string should be indistinguishable from a uniform random string. Okay, let's say S, which is uniformly random over the same length binary string space. So S should be indistinguishable from the PRG output. That is what PRG is. Now, what stream cipher is? The stream cipher comes into picture when we are talking about practical instantiation of PRG. There, we say that stream cipher has two algorithms. One is init. There, with the help of some seed or maybe some initialization vector, we generate the first bit of the output string. Okay, so this is some initial so this is seed and this is some initial state generated, and then there is another algorithm called get bits, where we say that using each state value it will apply some function and generate the next state value. Okay, so it will generate one after another a sequence of pseudo-random bits. Here, the length of output is fixed, but here you need not have any control over how long the output will be. So stream cipher will continue to generate pseudo-random bits. Okay, 0, 1, 0, 1, any binary value it will generate pseudo-randomly. So that is what stream cipher is. There is no restriction over the output length. Okay. Now coming to whether stream, so if you remember, PRG is deterministic, right? Because we know when we write a PRG, that G of S, this algorithm of G, what it does with the seed, it is public to everyone. So this is some public algorithm. What is unknown is the value of the seed S, right? Similarly, stream cipher is also deterministic. Okay. Now, what happens is that if you just write some basic encryption scheme using, I am adding another page. Okay. So there can be a basic encryption scheme using stream cipher, that is given a message M, you encrypt with a key K in this following manner, that G of K XOR M, and G of K will generate the link, this G of K is, if it is a stream cipher, it will generate a pseudo-random string of length same as the message length. Okay. Now, if this key is used for encrypting multiple message, what happens is that because you are not changing the key and your encryption scheme is deterministic, right? So you encrypt some another message M dash with the same key. Okay. This G of K value is same, right? Like this it will happen. So for same M, it will always output same C. If I denote the ciphertext as C, for same M, same C is generated every time because key is fixed. So for multi-message security, if you remember, there is this concept of multi-EAV security. So indistinguishability of multiple encryption in presence of an eavesdropper. What this game says is that you have some challenger, we say, right? And you have some adversary. Now, the indistinguishability game in presence of multiple encryption works in this way that adversary will provide to challenger two message vector. Okay, so M0 will consist of, let's say, some L number of messages, and M1 is another vector of messages consisting of, again, some L number of different messages. Okay, now it has to say that so challenger will basically decide upon which message it wants to encrypt. Okay, so it just tosses a coin and decides which message it wants to encrypt, and accordingly whatever B it chooses, corresponding ciphertext CB using the same encryption key, so this will be returned. Okay. So this is your capital CB, which consists of either this C1 to CL or C1 dash to CL dash. Okay, depending on which bit be it chosen. And adversary's job is to observe this ciphertext CB, ciphertext vector, better to say, and then decide what B was chosen by the challenger. In this case, if this is the encryption scheme, this is a deterministic encryption scheme. In that case, what happens is that it can never be secure against multiple encryption. Okay, why is that so? Because the adversary can choose your M0, M1 in such a way, so adversary can choose M0 to be in this manner. Okay, M0, M0, and M1 vector is this. Okay, now the ciphertext will be sent by the challenger, right? Okay. Ciphertext CB is returned to the adversary, which will be either of this form C0, C0 or of this form C0, C1. Correct? Because M0 always maps to C0 after being encrypted, and M1 always gets mapped to some other C1. Okay. So because your message vector chosen by adversary was in this form, either two messages are repeated or two different messages. Okay. Now seeing the form of ciphertext, whether first ciphertext of your ciphertext vector is exact same as second ciphertext of your ciphertext vector, or it is not the case, it can distinguish between these two cases. Okay. So whenever you have some deterministic encryption scheme that can never be secure against multi-EAV adversary. Okay. Why eavesdropper? Because it does not have access to encryption oracle. If you remember from last week, we discussed the security notion like ciphertext only attack, which is like eavesdropper thing, and there was KPA, known plain text attack, there was CPA, and there was CCA, right? With the increasing adversary power. So we are in the COS case where the adversary is allowed to just see the encryption of one ciphertext and it has to determine that which message it is encrypting under it. Okay. Also, one thing I should mention is that deterministic encryption scheme can never be secured against multi-AV adversary if it is stateless. Okay. What do we mean by stateless encryption? If it would have been a stateful encryption scheme, then what happens is that there can be some concept of counter. So M0, if you were encrypting it at time t, so there will be some information, maybe some counter value of that time, which is used in its encryption process. So its corresponding ciphertext will have the information of this state. Okay. And same message M0 when you encrypt at some other time. So that state information will be included in the encryption. So it will generate some other ciphertext. So M0 will be encrypted to different values depending on the state. In that case, we call it a stateful encryption scheme. But when we are talking about the fact that deterministic encryption scheme can never be secured against multi-AV adversary, we are talking about the stateless encryption scheme. Okay. So, so that means that the third statement, same key can be used for encrypting multiple messages in stream cipher. That is a wrong statement because stream cipher is deterministic and so same key cannot be used for encrypting multiple messages. Okay, that will break the security. And the fourth option says that stream ciphers are single message CPA secure. This is again wrong due to the same reason, because for CPA security, it is a required condition that the encryption scheme becomes randomized encryption scheme, okay, not deterministic one. Okay. So otherwise, what happens in CPA security? The adversary has access to encryption oracle, right? So for the message M, basically what can happen is that for the same message M, if it has observed the ciphertext C, then it can, in the challenge phase, when it gives the challenge ciphertext M0, M1 to the challenger, this side is adversary and this side is challenger, it has already seen the ciphertext corresponding to M and it never changes because it is a deterministic encryption scheme. So it can just query for corresponding this thing, okay? And now it sees CB and it can check whether CB is equal to C0 or CB is equal to C1. And with probability 1, it will win the game, right? So it has to be the case that the encryption scheme is randomized. Then seeing CB, CB will never be exactly equal to C0 or exactly equal to C1, except with negligible probability, of course. Okay. So that is why the fourth statement is also wrong. So am I clear, or if you have any doubt, you can ask. Okay, I think let me proceed to the next question. So just now we talked about multi-message security in presence of eavesdropper, right? So I think this will be easy to answer for you all. Also, this meeting ends in 10 minutes, so you can join back in the same meeting link. And if you are not able to do that, you can just wait for 10 minutes and then join back, okay? Now, Your next question is that comment on multi-message EAV security and multi-message CPA security of OTP scheme. OTP is, as you know, one-time pad, right? So you can answer in the chat. Just like multi-message EAV security, multi-message CPA security also works in the same way. Okay. So do you think that OTP scheme, one-time pad scheme, which is defined as, I think you remember, right? Encryption KM is just XOR K. K is uniformly random over some key space, right? And decryption is also happens same manner. So this scheme, is it multi-message EAB secure and is it multi-message CPA secure? In the multi-message EAB security, you just directly send, like the adversary directly sends two messages M0 M1 to the challenger, and challenger encrypts any one of them and returns to the adversary, and adversary's job is to determine which message encryption it has seen. And in case of multi-message CPA security, the adversary is allowed to do multiple queries over various messages of its choice, message vectors of its choice, and finally in the challenge phase it will send two message vector M0 M1 and see encryption of any one of them. So the query phase is allowed in case of CPA scenario, which is not the case of eavesdropper scenario. So you can answer in chat. Okay. So I think I should discuss the answer. So basically answer is that OTP OTP is not multi-message EAB secure, and neither it is multi-message CPA secure. Why is that? So as you can see that in the previous example also what I said is that in a deterministic encryption scheme, if it is stateless, then it can never be multi-message EAB secure. Simple. So OTP is also a deterministic encryption scheme. It is of course single message EAB secure that we had seen in the last week also. But because it is a deterministic scheme, it cannot be multi-message EAB secure. Okay. And for the CPA security case, see, OTP itself is not even single message CPA secure, okay, because it is not randomized. So for even single message CPA security, randomization is required. And if it is not single message CPA secure, then of course it is not multi-message CPA secure as well. Okay. No, actually, this whiteboard will be saved in my, at least I know that in my computer it will be saved locally, so I can share with you. So that folder link will be shared with you. Okay, so don't worry. Uh, Now, okay, so let me I hope this answer is clear. So let me just proceed to the next question. So uh, we are discussing third question, right? So let func mn be the set of all functions mapping m bit strings to n bit strings. Okay. Per n set of all permutation mapping n bit string to n bit string. So determine the cardinality of this set. Cardinality of the two sets. Okay. So cardinality is the number of elements in the set. So this is a very basic question. So I hope you can answer. Let me just clarify more so that you can answer yourself. So what I am saying is that func mn is the mapping of all m bit strings. Okay, so you have this input table and each of the output, okay, let's say this is the row of your input table which contains all the m bit strings as input, and each of them will output to a n bit string. So how many possible functions can be there of this type? Okay. So you can answer in the chat. M into n, are you saying? Uh, M is the number of bits, remember, okay? M is the length of input string, N is the length of output string. It is way more than M into N. Okay. Just think it again. Can the mapping be multi? Yes, there is no, it is not one-to-one mapping. It can be anything. It can be many to one also. M to the power N. Again, let me remind you that they all are binary string. We are talking about m bit binary string as input and n bit binary string as output. And anything can happen in the. Is my screen visible? Okay, thank you. So we were discussing this question. Uh, so would you like to change your answer basically? So I think I gave the first two set, asked for the cardinality of first two set. There are two more also. So you can just give the answer on your chat. Okay. So I can write it here. So what I was saying is that your func mn set has this m bit input and each of the output has length n bit, right? So you can view it in this way that your output table, right? What is the size of your output table? Bit size. So each of the number of rows in this left side table is 2 to the power n. That is easy to see, right? You have m bit input. So your number of inputs for number of total possible input is 2 to the power n. Now each of these inputs are mapped to one single n bit string. So what is the size of your output table? That is n into 2 to the power m. Am I right? So there are total 2 to the power m output rows as well. And each output row has bit length n. So this is your size of output table, right? Now, each of the bit of this output table can be filled up with either 0 or 1, right? Because we are considering the all possible set of functions that maps m bit string to n bit string. So this output table of size n into 2 to the power m bits can be filled up randomly with either 0 or 1. So there are two possible values for each of the bits, right? There are n bits for each of the output row and each position can be filled up with either 0 or 1. So that makes the total possible values or possible combinations in this output table, or in other words, the set of all possible functions that map m bit string to n bit string, that is 2 to the power n into 2 to the power n, right? So this is n into 2 to the power this quantity, right? Am I clear? Now, can you try to answer the next question that I asked for, that what is the cardinality of the set per n comma n, that is permutation of all n bit string. So that makes your input table also has size n and your output table also has bit length n. However, there is no repetition, right? Here I said that many to one mapping is possible, like this input, the output corresponding to this input can be same as output corresponding to this input. So many to one function was allowed in this case, but here as we are talking about permutation, so each of the 2 to the power n input will map to unique output here. That's why it is a permutation, right? So let's say when we talk about permutation, what do we say? Say 1, 2, 3, 4, 5. A permutation of this could be, let's say 2, 1, 5, 3, 4, right? So no value is repeated here, but each map goes like to unique values. Okay. So that's the case of permutation. Now, how many permutations are possible on n-bit string? That is our question. Okay. Would you like to answer the question in the same manner? Anyone in the chat? To the power, yes, you are correct. So it is 2 to the power n factorial. So if it is not clear to you, let me just explain once that your output table here has size, row size 2 to the power n, right? And each of the row can be repeated or can be permutated, right? So as you know, the rule of permutation, so 2 to the power n values can be placed only once but anywhere in this table. So that makes the count or cardinality of the set per n comma n as 2 to the power n factorial. Okay. So this is the correct answer for the second part. The third part says that if k mn are set of all keyed functions mapping m bit string to n bit string, right? So here the difference is that your input table still has size m bits and output table has size n bit, but the mapping is fixed for a fixed k. So let's say your key k has a bit length of L. Okay, let's say k is a fixed key which has bit length L. So it can be randomly chosen from this. So I should write. Uh, so your key k is a fixed string which is randomly selected from L bit length space. Okay, so your key has size L. Now, for a fixed k, your mapping is fixed. You vary the k, you get another output table. Okay. So how many number of functions can you define with such restrictions, right? Here you did not have any restriction. Okay. There is some random scratch on the screen. Ajit, can you just please remove that thing? Okay, thank you. Yes, so for fixed key, you get fixed value of this output table. All these bits in the output table are fixed for fixed key. So how many functions are there in this set? Denoted with fmn with k in the superscript. So if you notice, it all actually boils down to the how many values of key k possible, okay, which is nothing but 2 to the power n, because key k has bit length of l. So 2 to the power l possible key values are there, and for each of those key values there is a unique representation of the output table. That is why we can write that the cardinality of this set fmn with a key k, that is 2 to the power l, where L is the length of this key. Okay. Each key refers to one particular representation of the output. So similarly, if you go to the permutation part also, that if instead of function, it would have been the n bit to n bit permutation, then also it would be nothing but depending on the how many possible values of key are there. For each possible value of key, there is one permutation. So that would make the cardinality of this set also 2 to the power n. Okay. So let me proceed to the next slide. So this is a question on LFSR. linear feedback shift register. Okay. So assume a degree 6 LFSR is given with feedback coefficient C0 and C5 equal to 1 and all the other feedback coefficient 0. So you have to compute what are the first 10-bit output by this LFSR if it starts in this initial state, all 1. Okay. So what is linear feedback shift register? It is linear, right? So let's say we have a shift register, right? So we denote it with, let's say 0 is 1 till Sn minus 1 in bit shift register. And how does it work? So it will always, one clock cycle, it will output the last bit, that is S0. And there will be some random tapping position over here. Okay. Somewhere in between there can be tapping. So, and all of this value goes into the last value, right? So basically, at some point of time, so for the first n clock cycles, you will get S0 and then S1 till S minus 1. And then what you get is that, so for each cycle, this gets shifted, right? The values get shifted. So you get S1, S2 here, and the last bit, updated bit, becomes XOR of this tapping position, right? So let's say you have tap the position 2 and 3, then your Sn minus 1 in the next state becomes, so I plus 1th round value of Sn minus 1 is ith round value of S2 XORed with ith round value of S3. Like that it works, okay? And in each round, your last bit gets out, okay? So that is what LFSR is. Now, coming to this particular question, so you can work it out on your own, right? So there are 6 ones, okay? This is the initial value. So S0 to S5 are given here, and this C0 and C5 denotes that your first and last positions are tapped, right? S0 and S5. So at each round, so we start with this round 0, right? And in round 1, what happens is that this first and last bit gets jobbed, and they makes the new value of Sn minus 1, that is S5 as 0, 1 XOR 1 is 0, and the rest of the bits get shifted. So 1, 1, 1, 1, 1, and this one gets out. Okay. What happens in the next cycle is, again, these 2 bits gets jobbed. So 0 XOR 1 becomes 1, and rest of the bits just gets right shifted. Okay. And this one gets, so this one is this one comes out as this. This is the mapping, right? So like that, you can do the maths on your own to see what is the output after 10th round. So I think you can calculate this on your own. Now, is this LFSR maximum length? So how to answer this question? So you can see that the LFSR given here, we have tapping position at 0th and 5th value, or you can write it as first and 6th value of the LFSR. So we get the polynomial representing the LFSR as x to the power 6, x to the power 1, because first and 6th bit are 1, and there is this 1. So this becomes the polynomial for LFSR. And if this is a primitive polynomial, that will imply that LFSR has maximum length. So how to check if it is a primitive polynomial? That is, if this is an irreducible polynomial, that is, it can be factorized anymore on this binary Galois field, and this should divide the polynomial x to the power 2 to the power 6 minus 1 plus 1. Okay. If sorry, if this is divisible, then what happens is that uh, basically this should be the least degree polynomial. So this value uh, n should be the lowest value for which this particular form is divisible by the polynomial, then we call it a primitive polynomial, right? And if this is a primitive polynomial, then only we say that this LFSR has maximum length. Okay. So there is another question again from LFSR. So here we consider a nonlinear combination generator where we have a degree n LFSR, but the output at each time step is not S0, but instead some function g of S0 to Sn minus 1 for some nonlinear function g. Assume the feedback coefficient of the LFSR are known, but its initial state is not. Show that each of the following choices of G does not yield a good pseudorandom generator. So there are two possible nonlinear functions given to generate the next bit of the LFSR. So that actually, because this is nonlinear function, so it is not anymore linear. It is some feedback shift register. But anyway, so this is how you define, right? So here what happens is that your, again you have this shift register, right? S0 to Sn minus 1, and your Sn minus 1 of I plus 1th round is nothing but S0 of ith round and S1 of ith round. That is how we define for the part A. Okay. So do you think that this LFSR can be broken? No. Seeing the output bit of each round, okay, can you determine that this is the output of PRG or this is output of truly random generator? Okay, so let me discuss maybe. So as you can see here, uh, basically if this is the way how you generate the next bit of each round, you can see that 1 is generated with probability 1 by 4, whereas 0 is generated with probability 3 by 4. So clearly, if you observe the output of feedback shift register continuously, 0 occurs with a greater probability. And if you analyze that probability, you can clearly distinguish the output of feedback shift register from a truly random output, right? Because in that output string, 0 will occur with much higher probability than 1. Okay. Ideally, your 0 and 1 of output of the shift register should occur with equal probability. Otherwise, it is not indistinguishable from a random string, right? So we want it to be pseudo-random. That is, except with negligible probability, it is indistinguishable from a uniform random string. But this is not the case here. Because for any two combination of S0 and S1 values, 0 occurs with high probability. For the second question, the nonlinear function was defined in this way. S0 and S1 XORed with S2. Okay. So here you start with assuming S1 equal to 0. Okay. Then what happens is that in the first step, your output bit Y0 is written as S0 and S1 XOR S2. That is what it is defined, right? Now, if you assume S1 is 0, then S0 and 0 becomes 0, right? Ending any bit with 0 becomes 0. And 0 XORing with S2 gives you S2. So, if you just assume one bit of your initial state, then in case if you guess it correctly, you can see here that the sequence of bit S2, S3, S4, all the initial state bits are gradually known to you, right? The way the nonlinear function is defined. So, by seeing the output of feedback shift register, that is Y0, Y1, Y2, Y3 and all, and guessing the S1 bit to be 0, you can see the initial state bit S2, S3 to Sn minus n. And now, so you have a total of, you have S0, S1 till Sn minus 1, right? This one you had assumed, and assuming this to be 0, you got some values of these bits. Now, S0 you can guess to be 0 or you can guess it to be 1. Now, assuming that your seed was 0, 1 and whatever sequence of bits you get as the value of S2, Sn minus 1, and this is the first case. With this, you can check that with this initial state, what is the expected value of the next state, right? So the next, this is the initial state, right? This is the initial state. And what is the next n output bits for the next state that you can see. And you also assume the S0 to be 1, that is second case. And then you already assumed S1 to be 1, and accordingly we get some S2 to Sn minus 1 value. So this is another possible value of seed. And for this also you observe what is the expected value of next n bits. And you observe yn to y2n minus 1. If this matches with any of these, then the adversary outputs that the output is from a PRG, right? So if you remember, in a PRG game, the adversary has to distinguish whether it is seeing output of pseudo-random generator or it is seeing output of truly random generator. If this is the case, that is the next n state bits are matching with any one of these, then it outputs it as a PRG output. Otherwise, it says that it is a truly random generator output. Okay. And as you can understand that because it is just guessing the single one bit, right? S1. And with probability at least 1/4, if the challenger was actually outputting the PRG output, then with probability at least 1/4, the distinguisher wins. And if it was a truly random generator the challenger was using, then also it would have been win the game with a negligible probability. So the difference, distinguishing advantage between the two cases is not negligible. So with high probability or with non-negligible probability, the distinguisher will be able to distinguish this kind of outputs. Okay, so this is not a secure practical instantiation of PRG or secure instantiation of feedback shift register. Okay, so can I hope the explanation is clear. So maybe we can proceed to the next question. So one-way function the question asks which of the following is or are true for one-way functions. So OWF is deterministic function, OWF is randomized function. Any many-to-one function can act as OWF, or OWFs are necessarily injective functions. So you would like to answer? Okay. Kapil Dev is saying third option. Any many-to-one function can act as OWF. Mm, may not be actually. Okay. Um, First one, Abhirup is saying OWF is deterministic. Uh, Not necessarily. Like, of course, like you have a one-way function, right? So it is deterministic, but so yes, whenever we talk about function, so this is not mapping, right? So function is always deterministic. Whenever you talk about function, functionality has to be deterministic. Okay. Uh, so yes, Abhirup, your answer was correct. But many to one function, all many to one function cannot act as one-way function because one-way function has certain properties to satisfy. So this is computable in forward direction easily, but hard to compute in the reverse direction. That is why this is one way, right? So given some x from the input space, you can easily compute f of x. Okay. But given a random element from the output space, okay, whatever the range of fx is, given a random element from there, if you want to compute f inverse of y, this is hard actually. So uh, a particular many to one function can act as OWF, but not all. You have to cryptographically satisfy this security criteria to be a one-way function. Okay. You can find counter example for this, right? I think this is already discussed in your lecture videos also, that not all many to one function can act as one-way function. And OWFs are necessarily injective function, that is one to one. This is also a wrong statement because that need not be the case. As I said, that there can be many to one function which act as OWF, but again, that is not a sufficient condition. Okay. So, okay. If this meeting ends, then again you have to wait for 10 minutes and join back. Okay. Just reminding. Uh, okay. Here comes some interesting question on PRF. So, which of the following candidates is or are not necessarily secure PRF? So, the given assumption is that FKX, which has input size of n bit length, key size of n bit length, and output space also has n bit length size. Now, given such a secure PRF, whether these further constructions of PRF are secure or not. So GKX is given as FKX XORed with FKX bar. This is complement of the binary string, right? So 10 complement of 10 is 01, complement of 11 is 00, just the binary complement. Okay. So let us proceed with one after another. So about the first one, what do you think? Is it a secure PRF? So in PRF, let me just, I should maybe recap once that what PRF is. So what is a PRF? PRF is pseudo-random function. So what happens there in the security property? Again, there is this game between challenger and adversary going on. So adversary can query with some input xi, and in response, challenger will provide it the functional value for some particular key fkxi, that is the PRF output. So after doing this polynomial number of times, why polynomial? Because adversary, we already assumed in the computational world that the adversary is a probabilistic polynomial time adversary, PPT adversary. So it can at max query polynomial number of times to the challenger for inputs of its choice and see its corresponding PRF output. After this conversation is over, then the adversary has to determine whether it was interacting. So, okay, basically yi can be either fk of xi or can be uniform random string over this output space. Okay, let's say output has bit length L of n. So yi is just uniform random. So this can be the case with equal probability. So maybe it tosses a coin. Okay, if b is 0, then it outputs fk xi, and if b is 1, then it outputs a pseudo random string from a random string from 0 1 to the power ln. So either of this can be the case. And after this interaction is over, the adversary has to determine what B it used, whether it was output from a PRF or a truly random function. Okay. So now this is what PRF is. Coming back to this question, that given a secure PRF FKX, whether this construction GKX given as FKX XORed with FKX bar is secure or not. So remember, in PRG, you were not allowed to do any query or something. You are just able to see the output of pseudo-random generator. But in case of pseudo-random function, the adversary is able to see output, PRF output for several inputs of its choice. And then it has to determine whether it is interacting with a pseudo-random function output or it is interacting with a truly random function. Okay. So can there be any possible query, a possible attack where the adversary is able to determine whether GKX is PRF or TRF? So any answer from your side for the first one, I am saying for now. Yes, no. Is it secure? Last week we discussed similar questions for PRG, that given a secure PRG, whether the given constructions of PRG are secure or not. So here is the PRF thing. No. Can you explain? Maybe you can unmute yourself and explain why do you think it's no? Maybe explain the attack. Virup Sarkar. Your answer is correct. It is not a secure PRG, that is true. But how the adversary, what will be the adversary strategy to distinguish the output of GKX from a truly random function output? Okay, maybe I should explain. So what can be the, so there is answer in chat. Divide into two. Okay, divide into two parts. Divide into two parts. How? This is a XOR, right? What will you divide? Mustafa, can you explain? I think your answer is correct for the second option. There, because it is a concatenation, you can divide it into two parts. Yes, you are talking about two. That is okay. But yes, your answer is correct for option two. So let's see for what happens for option one, right? So here again there is the game going on, right? I'm again writing challenger and adversary. Okay, for question. So the adversary can craft its inputs in a way. So it first query with x1. Okay, what it sees is that fk x1 XORed with fk x1 bar, right? Next, it queries with x1 bar. So what it will see in the output? It will see fk x1 bar XORed with fk x1 bar of bar, that is x1, right? Now what you will see? This and this are exactly same, right? And this can be the strategy of adversary to distinguish. So this will be same when the challenger chooses to output the PRF value. But if it would have been chosen the output of truly random function, then they will never be same, right? Because in that case, output corresponding to x1 and output corresponding to x1 bar will completely be random things. Okay. So they will never be same in the PRF case, or will be same with negligible probability, right? So with non-negligible probability, the adversary is able to distinguish the output of PRF from the output of truly random function. So that is how the adversary can make its strategy to distinguish. So this one is not secure. And as already Mustafa answered, so this one is also not secure. So here what you can do, you can just you send x1, right? And what you see is that fk x1, I am talking about option 2, right? Question 2. So fk x1 concatenated with fk x1 bar. And then you query with x1 bar. Then if it is a PRF output, then it happens that fk x1 bar concatenated with fk x1. Okay, so if this is actually coming from a PRF, then second part of your first string will be exactly equal to first half of your second string, and first half of your first string will be exactly equal. So we were talking about this, right? That whenever you are just seeing the output of two cases, x1 and x1 bar, your first half of the first string will be exactly equal to the second half of your second string, and second half of your first string will be exactly equal to the first half of your second string by the way the PRF is defined. So if the challenger decides to output from PRF pseudo-random function, then the adversary will win with probability 1 in this case. And otherwise, what is the probability that adversary wrongly guesses the output to be PRF output when it was actually a truly random output? That is the case that when you have two random strings here, right? This is of length 2n and this is of length also 2n. So total 4n length string, if I consider both the outputs together, so 2 to the power 4n is the number of possible values that this 4n length string take in together. And what is the probability that the output was truly random, but it happened to be the case that this condition was satisfied in the output, that first half of first string is equal to second half of second string, and so on. So this happens with in case 2 to the power 2n, right? Why is it so? Because you are fixing 2n bits, and the second string is just depending upon the first string construction. So there are only 2 to the power 2n possibilities where this condition will be satisfied by these 2n length strings. Okay, so this is the probability when the challenger chooses to output truly random bit string, but the distinguisher wrongly guesses it to be pseudo random function output. Okay, so basically the distinguishing advantage between the two cases is 1 minus 1 over 2 to the power 2n, because this is 1 over 2 to the power 2n. So 1 is the probability with which, so if I write it formally, then it happens that probability when challenger outputs, sorry, I should write, okay. Erase it. So I am saying that probability that adversary guesses the bit to be, guesses the output to be PRF, when actually this is the conditional probability, when actually challenger chose PRF. This is one case, and difference with probability when adversary guesses to be PRF upon the condition that challenger chose TRF, truly random variable. So this first probability is 1 and the second probability is 1 over 2 to the power n. So overall this quantity we say it distinguishing advantage, right? Distinguishing advantage of the adversary. Okay, so this is not negligible. Okay, so that is why we say that the second option is also not secure. Now, third one, I think it is very easy to see. So you would like to answer the third one, whether it is secure or not. So fs of x is secure, but g of s is constructed as one concatenated with this PRF output. So will it remain pseudo-random function? You can answer in the chat. Let me erase these things actually. You can unmute yourself also, or you can answer the chat. Anyone? This is very easy to see, right? I think in the last class we discussed like G of S construction being G of S secured PRG, whether G dash S, which is defined as one concatenated with G of S, is it secure or not? That one we discussed, right? So what happens with the pseudo-random function case? Our final target is anyway to distinguish whether it is truly random or pseudo-random, right? So it is very clear, right? To see that if you always see a 1 in the end, right? Concatenated with the truly random, with the pseudo random output. So basically, what is the strategy of adversary here? So anything it queries, right, with xi. So if it is a pseudo random function output, then it will return fk of xi, right? Or fs of xi, whatever. So it can just see the output of a few polynomial number of queries, xi plus 1 and so on. And for each of them, if the challenger chooses to send PRF output to the adversary, then for all of these cases, 1 will be the first bit of the output, right? And if this is the case, then the adversary decides that, well, I am interacting with the PRF challenger. But if it would have been the truly random function output, then the first bit can be 0 also sometimes, right? So maybe with probability 1 minus half, with distinguishing advantage 1 minus half, the adversary actually wins this game. Why 1 minus half? Because if it was actually a PRF, then with this strategy, with probability 1, the adversary wins. But if it was a truly random function output, then adversary wins with probability half, because for a truly random string, the first bit being 1 has probability half. So the distinguishing advantage is half. So we can say that this is also not secure. Now the last one. Do you think this is a secure PRF or not? Just you can answer anything in chat. I'll wait for 1 minute for your answer. Otherwise, I can discuss. Okay, there is one answer. You were saying it is not secure. Then can you just say what will be the adversary strategy if it is not secure, you are claiming? Then what will be the adversary strategy to uh, distinguish? Like in the previous case we discussed. Okay. So basically it will be secure, right? Let me explain this here. What happens is that, let's say uh, you have you already have a distinguisher which is able to distinguish this PRF f dash, right? Which is defined in this manner. So if k of x is already secured PRF, and your f dash is defined as f of x with fk of x as its key. Okay. So let's say that there is a distinguisher d dash who is able to distinguish the output of f dash from a truly random function output. Then using that distinguisher d dash, we can design another distinguisher d who will be able to distinguish output of fkx from a truly random function output, which in turn implies that f is not a secure PRF. But we know that f is a secure PRF. So by contradiction, we can say that f dash is secure. Otherwise, f dash is insecure, or f dash is a not secure PRF will imply that f is also not secure. So by contradiction, we will prove this. So let's say what will be the strategy of distinguisher D to use distinguisher D dash to distinguish between output of fkx from output of truly random function. So here is this challenger or verifier. So challenger denoted with ch or verifier denoted with v, they are the same thing. So this entity first decides whether it will provide outputs from a truly random function or output from a pseudo random function. Truly random function is denoted with t. So if b is 0, it outputs pseudo random function, or if b is 1, it outputs truly random function. Now, first query is coming from the adversary or distinguisher d dash. So it will query with some x, right? The same x is forwarded by distinguisher d to this verifier, and some y is returned. Y is either of the form fkx or of the form dx. Now, whatever y it receives, now distinguisher d dash also chooses one bit, b dash, and if b dash is 0, then it will form y dash in this manner, f of x with y as key. So remember, if b is 0, then y is of the form fkx. Then y dash will of the form f of x with key as fkx, right? So this will satisfy the construction of this PRF, f dash. If b is 0, then if b is 0 and b dash is also 0, then y dash has the form of output of f dash. Okay. And if b is 0, then we just forward the same y to d dash. Okay. So there are 4 cases, as you can see. Only 2 cases we are concerned about, that is b is 0, b dash is 0, then y dash has the form of f dash. Okay, that is the output of f dash. And if b is 1 and b dash is also 1, then also it sends to d dash a truly random value, right? Now, clearly in the view of the distinguisher d dash, if it is able to distinguish between these scenarios and correctly output b double dash, that will imply that d will have to check whether b double dash is equal to b dash. So, if d dash is able to correctly distinguish between these 2 cases, then d also will be able to distinguish between the PRF and TRF cases for the original PRF, right? So probability of D's winning is exactly equal to the probability of D dash winning. So that will imply that if D dash wins with non-negligible probability, D will also wins with non-negligible probability, thus making F in not secure PRF. But we already are given that F is a secure PRF, so we say that F dash is also a secure PRF. Am I clear? So whenever you are proving something to be not secure, then you have to show some adversarial attack strategy with which you can distinguish the 2 cases with non-negligible probability. And if you are claiming some construction to be secure, then you have to show that in a contradictory manner, that if this is not secure, that would imply some base construction to be also not secure. But because the base construction is secure, you will conclude that the proposed construction is also secure. So I think I can proceed to the next question. So here we are talking about some encryption algorithm. So there is a secure PRG given which outputs L bit length string with seed having length n. and we construct a keyed function fk. So this is both input and output space are same for this keyed function, and defined as fkx equal to gk XORed with x, and use fk to design an encryption algorithm for encrypting message of length L bits. So encryption is defined in this manner: r comma fkr XORed with m. Okay. So as you can see, this algorithm is randomized algorithm, right? So there are some comment on single message COA security, single message CPA security, and multi-message CPA security of this scheme. So let's proceed with one by one. So what do you think about COA security of this scheme? Is this scheme COA secure or single message secure in presence of an eavesdropper? Anyone answer in the chat? Okay. So maybe let me discuss. Uh, so this, as you can see, this is a randomized algorithm, and for in case of single message COA security, what happens is that you just get to see one single ciphertext, right? And you have to determine whether that ciphertext is an encryption of M0 or M1. Now, because for each different encryption, your R is selected randomly. So that part actually randomizes this whole thing, right? So you cannot basically infer any extra information about the message by seeing the ciphertext, because FKR is nothing but a kind of encryption of X. You can think of like FKX defined as GK XORed with X, right? So if X would have been a message, XORing it with a output of pseudorandom generator would make it like a OTP scheme. So for single message COA security, this is a pseudorandom bit string FKX, and then again you are XORing FK of R, where R is random, with M. So this retains the COA security. Okay. But what happens with CPA security? So in case of CPA security, you can see that, let's consider one case that if you would have, because in CPA security, the adversary is allowed to do multiple queries, right? And it has access to encryption oracle. So it can query with this plain text, M being all 0. Then the response ciphertext would have been some R, and corresponding second part would be G of K XORed with R XORed with the message, that is 0 to the power L. Now, XORing with 0 means nothing but this string only, and R is also visible from the output part. So the adversary can XOR the second part of the output to the first part of the output to get the value of G of K. So that basically reveals the exact value of G of K. And then for any other message, okay, uh, the adversary can easily check whether this value, so it knows the value of GK, it knows the value of R, so it can clearly see the value of MB, the chosen message, right? So with probability 1, it can actually attack the system and retrieve what exact underlying message is there. inside that ciphertext. So it is not even single message CPA secure. And because it is not single message CPA secure, then of course it will not be multi-message CPA secure. Okay. So uh, let me proceed to the next question. So let pi uh, consisting of three algorithms, key generation, encryption, and decryption, be a symmetric key encryption scheme. Consider a variant pi dash where key generation algorithm remains same, but encryption and decryption algorithm changes in a way that encryption dash of m is defined as encryption of reverse of m. So instead of encrypting m, you are encrypting reverse of m. So what do you think? So if pi is CPA secure, does pi dash is also CPA secure? And if pi is COA secure, does that mean pi dash is also COA secure? So for both the single and multi-message case, you have to answer. So pi is given depending on whether pi is single message COA secure, multi-message COA secure, or CPA secure. You have to say whether pi dash will also hold that same amount of security or not. Okay, this is some answer by someone. You can answer in chat actually. This is saying A. Okay. I'll wait for other answers also. Your answer is correct, by the way. Okay, let me just discuss. So yes, for single message UA security, as you can see, so encryption scheme does not vary, right? It just does the encryption of reverse of M instead of M. So formally, if we have to argue that pi dash is also secure, what we need to show is that if pi dash is not secure, that would imply pi is not secure. Then by contradiction, we can say that pi dash is secure. So formally, how to do that? So let's assume that pi dash is not COA secure. Then adversary, that would imply that adversary is able to learn extra information about the distribution of underlying plain text, which is reverse of M. So if the adversary is able to learn extra information from by seeing the ciphertext about the distribution of reverse of M, then that would imply gaining extra information about the uh, distribution of the M itself. Okay, if you are reverse is what? So you have say string 110, the reverse of it is 011. Now, if uh, apart from the a priori information about the message space, by seeing the ciphertext space, the adversary is able to gain extra information with non-negligible probability about the distribution of reverse of the plaintext space. Then it is also able to infer extra information about the distribution of message itself. Okay, so that would make the scheme pi COA insecure. But we already know that pi is COA secure, so we conclude by contradiction that pi dash is also COA secure. Now coming to the CPA security, again our argument proceeds in exact similar manner. We assume an adversary A dash which is able to break the single message CPA security of the scheme pi dash. Then what happens? So adversary queries with some MI and adversary A just reverse it and provides it to the verifier or challenger. Challenger gives back encryption of reverse of MI, and this CI is forwarded to adversary A dash. So in the view of adversary A dash, it is seeing the encryption according to the encryption scheme pi dash. A is seeing encryption according to scheme pi, because here this is the input, this is the plain text, and this is the cipher text. So reverse of MI itself is the plain text here, and encryption K of reverse of MI is the cipher text. So in the view of adversary A, it is playing the game according to the scheme pi. But in the view of adversary A dash, it is playing the game of CPA security for the scheme pi dash with A. So in the view of adversary A dash, A is the challenger, but in the view of adversary A, V is the challenger. Okay. So like that, this game proceeds, and then whatever distinguishing bit A dash outputs, let's say B dash, it just forwards the same result to the verifier V. Now, if ADAS wins with non-negligible probability, that is, ADAS is able to distinguish between encryption of M0 and encryption of M1 with non-negligible probability, then A will also be able to do the same for the encryption scheme pi. And that would make pi a not secure, not CPA secure scheme, right? But then again, by contradiction, we say that because pi is already given to be CPA secure, pi dash will also be CPA secure. Okay. Now coming to coming to the multi-message, I think there was the part multi-message. There was not multi-message CPA security, but let me just mention that if a scheme is single message CPA secure, then it is also multi-message CPA secure, right? Because in the CPA security, you already query for multiple plain text, right? And see the corresponding cipher text. The adversary already has the encryption oracle access. So anyway, single message CPA security is not uh, very much varying from multi-message CPA security. In fact, they are equivalent concept. Why? Because in single message CPA secure game also, the adversary is allowed to see encryption of multiple plain text of its choice. Okay. So single message CPA security implies multi-message CPA security. Okay. And now proceeding to the next question. Consider an encryption scheme where encryption is applied twice on the plain text to make the system more secure. Consider a basic encryption scheme pi, again with these three algorithms, chain, encryption, and decryption, and then modify it to design pi dash, where chain is remaining same, encryption dash is defined in this way, encryption of encryption K of M. So this is like double encryption. You encrypt it once with key K, and you encrypt it again another time with the same key K. So this is like double encryption. And now analyze pi dash to answer the following. Describe the decryption algorithm and correctness of pi dash. So if this is the encryption algorithm of pi dash, how will you decrypt this ciphertext? That is pretty trivial, right? So you will first decrypt with key K and then again decrypt it with key K twice, right? So this is how you decrypt. This is clear, I think. And the next part of the question is check whether pi dash is CPA secure if pi is CPA secure. So do you answer this question? Anyone in the chat? So you have to comment on int CPA security and int EAV security. Indistinguishability in presence of eavesdropper, indistinguishability in presence of encryption oracle. Okay, maybe I should discuss. So again, we actually show that how existence of an adversary which is able to break the end CPA security of I dash can be used to build another adversary A which will be able to break the CPA security of original scheme pi. So how does it work? So the picture is bit congested, but let's say so. So the game starts from here. A dash and A plays the game CPA game for scheme pi dash, and B and A plays the game for CPA security of pi. Okay. Now A dash sends some message MI to A, and A forwards this same message MI to V. In response, VI sends ciphertext CI, which is encryption of MI under key K. Okay. Now this adversary again sends CI as another plaintext to V and gets back CI dash as encryption of CI under key K, which is nothing but encryption of KMI. So this is the double encryption result, CI dash. And it sends CI dash to A dash. So in the view of adversary, for plaintext MI, it sees ciphertext CI dash, which is the encryption according to the scheme pi dash. So for each plaintext query by the adversary A dash, adversary A has to query twice to get CI dash, raise query twice to verify V. Okay. And it sends CI dash. So this thing can be repeated polynomial number of times. This is the query phase, MI and CI dash, and this side MI and CI. So if there are n number of queries in this pi dash game, there will be 2n number of queries going on in this pi side. Now in the challenge phase, adversary A dash will send two challenge messages M0, M1 to A. And again, there will be 2 times query going on. First time CB will be encryption of some MB, any one of them will be encrypted in CB, and then A queries back with CB and gets back encryption of CB under the same key K. So CB dash is according to the encryption scheme pi dash. So this is encryption of MB according to pi dash. And if A dash is able to determine with non-negligible probability the value of B dash, that is what B was chosen by the verifier. So is it seeing an encryption of M0 or is it seeing an encryption of M1? With whatever probability A dash can answer this question, with the same probability A also can answer the question to verify. So they win with exact same probability. Now, if A dash has non-negligible probability of winning, that implies A also has non-negligible probability of winning, but this is not the case. Hence, we conclude that the scheme pi dash holds its CPA security, right? Now, coming to eavesdropper indistinguishability in presence of eavesdropper, we will present a counter example, right? So consider the OTP scheme. So we already know that if pi is OTP, then it is a single message EAV secure scheme, right? Now, if we double encrypt using OTP, so encryption dash becomes encryption of encryption M, which is K XOR M. That gives nothing but M. So it gives back the message itself. Whatever key value it had chosen in the keygen phase, the ciphertext always is same as the plaintext. Clearly, this leaks the whole information about the underlying message. So this is clearly not EAP secure. which implies that if pi is EAV secure, pi dash is not necessarily EAV secure. So that is the conclusion of today's session. If you have any query, you may ask. Otherwise, I can end this session. And as I mentioned in the beginning also that from the next week onwards, we will discuss the assignment questions as well. Okay, so I think no question, right? So let me end this session here then. Thank you for joining, and again, try to be interactive, and please join again next Saturday from 6 p.m. Okay? Thank you.